Good morning, good afternoon. My name is Professor Duke Orata. We are continuing with our discussions in thermodynamics. And today we want to look at one of the most important cycles. It's called the Otto cycle. Remember, we've talked about the internal combustion engines. We have talked about the four-stroke engine, and we have also talked about the two-stroke engine, that is the Van Cal engine. Now, in the four-stroke engine, we know we have the pistons and we have the different strokes. We have the different strokes, the intake, we have the compression, we have the power stroke and the exhaust strokes. So you remember all that, and we have the piston move up and down between the BDC and TDC. That's the bottom dead center and the top dead center. That constituted the stroke, the swept volume. These are now concepts which we have talked about. So let us look at the Otto cycle today. Let us discuss it in light of the pressure volume temperature diagram, pressure volume diagram, pressure, cylinder pressure, and we want to look at the volume, cylinder volume, and the kind of diagram which you get. So let's try to draw it as best as we can. State point 1, state point 2, state point 3, state point 4, 0, and then on the temperature entropy diagram or matrix, entropy, state point 1, state point 2, state point 3, state point 4, 4. So we have 4 processes in the Otto cycle. Like we have said, this is one of the most important machine cycles. In all motor vehicles, all those are based on Otto cycle. And you know the number of motor vehicles which are used worldwide in terms of transportation and so forth. Now, in this Otto cycle, we can clearly identify that we have several processes. We have cylinder pressure, we have cylinder volume. So we notice that this particular process here, this is a constant volume process. So that is delta V is equals to 0. That is constant volume. See it here as a constant volume. Constant volume. This one here also corresponds to constant volume. That's from state point 4 to 1. State point 4 to 1 is also a constant volume process. And if we look at process 1 to 2, that is isentropic. So 1 to 2 is isentropic. And this is isentropic compression. And remember, we said that from Closures inequality, where ds is greater or equal to dq over t. So if this ds is 0, then dq is equal to 0. So it means that process is adiabatic. It's reversible and it's adiabatic. So that means that for that isentropic process, there is no heat transfer into that system or from that particular system. and that is isentropic compression. That is for process 1 to 2. This isentropic. Isentropic. And then we have the other process here. This is isentropic expansion. That is 3 to 4. 3 to 4 is isentropic also. Now, let us discuss these processes systematically. The processes in this particular system. And the best thing is to look at them in terms of their process steps. So we have step 0 to 1. What is that step? 0 to 1. That's step 0 to 1. At that particular point, we have the intake valve open, and there's intake of air into the system. Because remember, there's going to be a fuel mixture, fuel air mixture, which will be ignited, and of course, then there will be combustion. Don't forget that. That's the air fuel. So this is the intake of air into the system, and notice that the pressure is constant. This pressure here, let's call it P1, is constant. So this is the intake of air into the system at constant pressure. And how are you going to take it? If you remember the internal combustion engine, we had drawn the piston. We had drawn the piston. Let's just have it there. So we had the piston. We have the piston rod. This is the piston. Let's just assume, let's just put it and say that is as BDC as opposed to TDC. Let's put TDC there. And we are talking of this piston as we are having valves. This is inlet valve. We had outlet valve or exhaust valve, outlet valve, and of course we had the spark system. It could be compression ignition system, or it could be spark ignition system. I kindly encourage you to go back to some of those lectures, look for them, and then just sit down and view them and look at them, understand. It helps quite a bit. Now, so what we are saying is that you have intake of air into the system at constant pressure. And so for air to come in, it means that the intake valve must be open. The intake valve, you can call it intake or inlet valve, is open. Now, let us look at the next step. At state point 1, that's a position described by thermodynamic variables, whether it's pressure, volume, temperature. So we normally call it state point. State point. So at state point 1, we have isentropic compression. What is compression? Compression is reduction in volume. That is, for example, when the piston is moving up from BDC to TDC. So that if we draw this system, this will be TDC, that's the top dead center, and this corresponds to BDC, that is the bottom dead center. So as you move from bottom dead center upwards, you are compressing the system. You're compressing the system. So at this particular point, at the BDC, we have the maximum volume in the cylinder. Don't forget that. Your maximum volume in the cylinder. And so you compress the cylinder. In other words, it's moving upwards. It's moving upwards, compressing the air-fuel mixture, or what you call the charge in that particular system. So it's compressing it and moves up to point 2, where we are at the TDC. So that's, let's look at 1 to 2. 1 to 2, what are we having? We are having isentropic compression. which is basically adiabatic. We have seen that from the Clausius inequality, which is basically adiabatic. As we do that compression, the piston moves from BDC to TDC. And if we look in parallel with the temperature entropy diagram, you clearly see that it's isentropic. It's isentropic. In other words, the entropy is not changing. The entropy is not changing. But there's a change in temperature. You notice that the entropy is not changing, but there's a change in temperature. There is a change. A change in temperature. In other words, in actual, it's increasing as we compress our system. So we have seen that as we compress our system 1 to 2, look at that, it's isentropic, and there's change in temperature. There's change in temperature, and of course the volume is decreasing. Now, we need more of this space, so let's work on the next step. But we need to point out something here. At this particular point, we have the compression ratio. We have the compression ratio. We started at V1 and we ended at V2. So the ratio of the two volumes gives you what we call the compression ratio. V2 over V1. That is the compression ratio. The compression ratio here is V2 over V1. Now, let us go to the next one here. The step 2 to 3. The step 2 going to 3. So we are at 2 going to 3. Notice one thing, this is an isochoric step. In other words, the volume is not changing, it's constant volume. And during this point, 2 to 3, remember the temperature is changing, the temperature is still changing, and of course we have ignition of the system at some point in this particular stroke here. That is, we are going to have ignition of the system at some point and this particular stroke here. So we have our compression stroke, we have had our intake stroke, so we are moving on to the power stroke. So step 2 to 3 is the process is isochoric. That is, the change in volume is 0. And then we are going to inject heat into the system. The ignition, we are going to inject heat into the system, and heat is added to the system. You have ignition at that point. And notice 2 to 3 is not isentropic, it's just isochoric. Now, so once we ignite our system, we have the power stroke, that is 3 to 4. 3 to 4. 3 to 4. So we have 3 to 4. In fact, sometimes for 2 to 3, there are cases where it's referred to as the explosion ratio, which normally sometimes is given by P3, pressure 3 over pressure 2. But I don't want to put too much emphasis on the word explosion ratio. But it's normally considered as pressure 3 over pressure 2. So let us look at the power stroke. That is 3 to 4. Very important step. That's the power stroke. This is the heart of everything. The power stroke. That's where now when you have ignited the air fuel mixture, Then, as a result of the combustion, you generate high pressure gases which push on the piston. It pushes on the piston. And when the piston is pushed, of course, we have the connecting rod. The connecting rod is connected to the shaft, and so the linear motion becomes it becomes reciprocating and so forth. We have seen this in several of those systems we have talked about. So we don't need to belabor, and so kindly I encourage you to look at some of our lectures. Then it will help you clarify things. But this is the most important step in this particular system. And it's an isentropic expansion, and of course adiabatic. Heat does not get into the system, out of the system. So this is an isentropic expansion. The high pressure gases push down on the piston. Ready to work. So we have work. That's a very important point. That's a very important point. So we have seen it is isentropic. It's isentropic expansion. So we have it here, isentropic expansion. That particular step there. Now, what happens after that? You notice that at that particular point, then we have step 41, which is basically the exhaust shock, where we are releasing. We add the exhaust. That's step 41. So we notice that step 41, we are now come to the BDC. We are releasing heat. Heat is being rejected. And this heat which is being rejected, it can go to the exhaust where it goes to the atmosphere. Pay attention. It can go to the exhaust where it goes to the atmosphere. And in most of the engine system, we have the cooling system. The cooling system, that's where we have the radiators. We have radiators. These are units there where you normally, fluid is added. Normally you have a coolant added in traditional old vehicles. A lot of them, they were adding, water was added to the radiator. And the radiator has some very fine fins made of very easily materials which allow heat to flow across. It's like a diathermic container. In other words, they are materials which allow heat to be transferred from the system to the surroundings and so forth. And so thermal transfers will mostly be from high temperature to low temperature before you achieve thermal equilibrium. So whatever gases heat is rejected, it can be handled, it can be absorbed, or the cooling system in the engine, that is the cooling system in the engine, acts as a sink for that heat, and some are actually released through the exhaust pipe. So there's heat rejected at this particular point. 41, there's heat rejected. And that particular process occurs under constant volume. It's rejected under constant volume. And it can go to the sink actually. Where it should go to can be the engine cooling system. Or it can come out through the exhaust system, which in industry, some of them is called a stack, where it's able to release those gases, the products of combustion. So, very important, note that at this particular point, we can say that heat is being put in, being inputted, say here, it out, being rejected. Yet is inputted and is rejected. Now, want to bring a more diagrammatic illustration of this process, Just want a diagrammatic illustration of this process which will help you understand it better. So if we have this our system, we have those quadrants there, 1, 2, 3, 4, 1, 2, 3, 4. Now, Let us say that is the top dead center. And this is the bottom dead center. So we said 0 through 1, we have the intake valve open. So let's just get a point where we have the intake valve open. Let's call that degrees theta 1. Theta 1. This is the intake valve open. And of course, it will be closed. At some point when now we have the power stroke and so forth, this is the intake valve closed. Now, the next step we talked of is the isentropic compression. So we have compression. So we have compression. As we are compressing, we are moving the piston from the BDC to the TDC. Remember that. BDC to TDC. So we can recraft that here and say that is our compression. Let's call that compression. We are calling that compression. And then the next step, we have our compression. Then we have, let's mark our exhaust valve. Exhaust closed. Exhaust valve open. So we have our compression. So the next one will be our power stroke. Our power stroke, that point, we can represent it as that. But remember, before the power stroke, we will have some ignition at that point. Because the ignition is not exactly at the TDC. Let us say the ignition, let's call that theta 2. Ignition.